Alright, so here we are with the 6-4 notes for geometry. We're going to talk about properties of special parallelograms. So we're going to go from four-sided shapes to parallelograms, and then now to special parallelograms like rectangles, rhombuses, and squares. Just to get us started, I want to kind of review what we have done so far. So there's this flow chart that we're going to go over here. So the idea of four-sided polygons, or just polygons in general, is that from a polygon, so any two-dimensional shape, you can go to having four-dimensional shapes. Four-sided shapes. Four-dimensional shapes would be something moving through time. Okay. And so from quadrilaterals, which is what we'd been doing, we moved on to parallelograms. And so parallelograms have these 7 traits that we went over. And then today we're going to be branching out from parallelograms to rectangles, rhombuses, and then ultimately squares, which is just a combo of a rectangle and a rhombus. So that is the idea there. So as we look at this, hopefully you can then fill in like these pieces of polygons. So taking a look at my filled in version here, you can see that in polygons, your interior angle formula is this guy right here. Now, if we were in class, this would be something you'd use on a test or a quiz, or you'd have next to you. So I would hope that you have kind of a sheet of paper that you can draw this on. We also have your exterior angles that add up to 360 versus interior has that formula. So that's just a polygon, any shape, two-dimensional shape. Then we went from there to four-sided shapes, so quadrilaterals have 4 sides, and they also have an interior sum of 360 degrees. So it is exactly this up here, but of course we've plugged in a 4, because there's 4 sides. The next piece here is your parallelograms, and again, this is what we've been going over so far. So the first one here is that we have opposite sides that are parallel by definition. We also have opposite angles that are congruent, opposite sides that are congruent. Consecutive angles are supplementary. Diagonals can bisect. And then when we moved on to proofs, we also talked about how one pair of sides can be parallel and congruent, and that will be fine. So kind of a combo of the first two. And then the last one where one angle is supplementary to both of its consecutive angles, which is kind of this idea here, but in proof format. So these two here are what we're going to go over today, so you can fill those in as well, but that's the idea. Our future lessons will be going a little bit more over trapezoids and isosceles trapezoids, and also kites will be in there as well. So heading back to our notes, our first piece here is a rectangle, and so a rectangle, of course, we know a lot about them. They're one of our basic shapes that you're kind of introduced to as you go through school. So we do know a lot about rectangles, but I just want to be very clear about what is and is not a rectangle, because a lot of times things are assumed that can't necessarily be assumed. For instance, unless there's any actual boxes in your rectangle, you cannot assume that what you are seeing pictured is a right angle. You have to actually have that piece there or something telling you that. So the first piece here is kind of by its definition, if you will. A quadrilateral is a rectangle if it is a parallelogram. So, sorry, I read that wrong. If a quadrilateral is a rectangle, then it is a parallelogram, meaning that it's a subset of parallelograms. And so that was that whole flow chart. If you have a parallelogram, you could have a rhombus, or a rectangle, or eventually a square, but definitely if you have a rectangle, you have a parallelogram. You also have a quadrilateral, like was on the sheet, and you also have a polygon. So that's the idea, is that rectangles are kind of a subset of a rhombus. Of a parallelogram. So that's what that first one is saying. It's a subset. And then this next one here, if a parallelogram is a rectangle, then its diagonals are congruent. So this one I always found interesting because we actually were fixing my basement at our previous house, and my dad was putting in some trim and setting up for walls and things like that. And he said that one of the tricks of your contractor is to actually measure from the top of one of your doorways to the bottom, and then the top to the bottom as well, because those pieces should be congruent. If they're not congruent, then you don't have a rectangle, because you'd think maybe you could measure this side and this side, but remember that one of the ideas of a parallelogram is that the opposite sides are congruent. So potentially you could be putting a very rectangular door into a parallelogram slot, which you would not want to do. So again, instead of measuring each side and saying, oh yeah, it must be a rectangle because they are opposite and congruent, that actually could potentially not be a rectangle. So, interesting. So again, a quadrilateral is a rectangle, and once it's named a rectangle, it can be a parallelogram, and therefore all of the qualities of a parallelogram. And then it can also be measured by its diagonal lengths. Alright, so this next one here, a woodworker is constructing a rectangular picture frame so that JK, let's see where that is, J to K, is 50 centimeters. That is the weirdest looking 50. Okay, there. And JL is 86. JL. Okay, and we need to find HM, so that's this piece here. So remember that we are being told that it's a rectangle, and so from that we have a lot of subsets of things that we know. For instance, we know that they're all 90-degree angles. We know that the diagonals are congruent, and so if this entire thing is 86, then this entire thing is also 86. Doesn't necessarily help us get exactly what HM is, but remember that from the subset of being a rectangle, we also know that a rectangle has a parallelogram properties. And one of the parallelogram properties is that the diagonals bisect. And so if the diagonals bisect, then this piece and this piece are going to be half of 86. And so half of 86 is 43, and therefore we know that HM equals 43 centimeters. So again, that idea that once you know that something's a rectangle, you also know it's a parallelogram comes in handy here. Alright, then we have our rhombus, which of course, up until probably recently, you've called it a diamond. Well, that's great, except it's not a diamond, okay? It's a rhombus. Also, rhombus in plural can technically be rhombuses, but then it also can be rhombi. So, depending on what you want to do with that, I use both, depending on how fancy I want to be. Okay. So, here is our image of a rhombus. Notice that each of the sides has a tick mark on it. That's because not only is it all of the properties of a parallelogram, it's also that all sides are not necessarily opposite and the same, but actually all the same. So that's what's happening in this first one here, kind of a definition here. A quadrilateral is a rhombus, so you have a four-sided shape that's a rhombus that also has the properties of a parallelogram. So again, that one is going from this idea that a rectangle has parallelogram properties, but also rhombus has parallelogram properties. The next one here is a parallelogram has diagonals that are not only going to bisect each other like any other parallelogram, they're also going to meet at 90 degrees. So that is a very interesting moment. They're perpendicular. Alright, and then the last one is that these diagonals that we're talking about actually bisect the opposite angles. So this piece here of angle B, part 1 and part 2, are equal. Part 6 and part 5 are also equal. So angle bisectors come from those diagonals. So all these pieces of the angle are congruent. Alright, so taking a look at an example here, remember if it says it's a rhombus, it also means that it's a parallelogram as well. So just so that we know when we see rhombus, we also will have properties of parallelograms. And we need to find TV. So where's TV? So that's this side length here, which would be the same for all of them, right? Because it's a rhombus. So in that case, we know that VT actually equals the same as XT, and also actually equals the length of WV. And so algebraically, we're going to set up that XT, which is 3B plus 4, is equal to WV, which is 13B minus 9. Alright. So if we set them equal, let's see, I'll add a 9 over and get 3B plus 13 equals 13B. Then we can move our B over, so subtract a 3B over here. Divide by a 10, and we end up with a B of 1.3. So if we know that B is 1.3, we can just plug it into our side length here, since B was 1.3. And we can multiply out those values. Just grab a calculator here. Alright, 13 times 1.3 minus 9 means that we have 16.9 minus 9, or 7.9. And so that equals VT and equals XT and also WV, and then the other side, WX. Alright. So then the last piece, again, is that you have a square. And a square is both a rhombus and a rectangle at the same time. So they just decided to name it a square instead of a rhombectangle or something. Which is just as easy as square, I assume. So it's a quadrilateral with 4 right angles and 4 congruent sides. So it takes that idea of a rectangle and a rhombus and puts them together. Alright, so a square is a parallelogram, of course, and so all of those parallelogram properties, like diagonals bisect each other, consecutive angles are supplementary, that kind of thing happens. And so a square has properties of all 3 of these, because parallelograms can also be rectangles and rhombuses, and so therefore all of those properties happen. So for instance, like we just learned with a rectangle, these diagonals are going to be congruent lengths. We also know that these angles are going to be bisected. So there's kind of a lot of things that kind of go within that definition. So we're going to show that the diagonals of the square EFGH are congruent, perpendicular bisectors of each other. So that's kind of a lot of things. Congruent, meaning I'm going to need the distance. Perpendicular, which means I'm going to need the slopes. And then bisectors, meaning I'm going to need halves of the distances. So we kind of need a lot of pieces here. And so we will do this. Alright. So the diagonals are named, I covered it up just now, FH. So one of our diagonals is FH. And so I need to find the length of FH, and I also need to find the length of EG. So in order to find the length of something, I need the distance formula, and so hopefully we remember the distance formula is going to be the square root of the 2 x's subtracted and squared, and added to the 2 y's subtracted and squared. Now, if you don't remember the distance formula, you'd rather not do that, you can also imagine that this is a right triangle. So for instance, we can kind of picture this very skinny right triangle with a little right angle right here, and this is our hypotenuse. So we could just find the length of the hypotenuse of a right triangle. That's actually more likely of what I would be doing, but I do want to show that we can use the formula, so I will do that as well. So, to find the length here, I'm going to label these as x1, y1 and x2, y2, and I'm going to subtract and add and all that good stuff. So I'm going to take my x2, which is 0, and subtract that from my x1, which is -1, and square that, add it to my y2, which is -4, and subtract my y1, which is 3. Square that. So if we go ahead and solve that, we actually end up with 1 squared. That's going to be added to -7 squared. And so we'll have 1 plus 49. And so we get the square root of 50. So that's the length of FH. Then I want to find the length of EG. And so the length of EG has an x1 and a y1 here, and an x2 and a y2 here. And so if we fill that in, our x2 is 3, x1 is -4. Add that to our y2, which is 0, minus our y1, which is -1. Putting those together, it's really 3 plus 4, so we have 7 squared here. And to that, we're going to add 1 squared. And so as you can see, we match up and we get 49 plus 1 again, which is the square root of 50. And so because of that, we do know that these two are equal lengths. And so we have just said that they are congruent. Perfect. The next piece is that they need to be perpendicular, and so perpendicular means that you have opposite reciprocal slopes. So we need to find the slope. So we need slope of FH, and we also need slope of EG. So let's see, we have a rise of FH of, where am I here? Oh, a run. So we've got 1, 2, 3, 4, 5, 6, 7 down and over 1. So -7 over 1 is our fraction there. And our slope for EG is rise 1 over 1, 2, 3, 4, 5, 6, 7. So positive 1/7. And so hopefully you can see that these two are perpendicular. We have opposite reciprocal slopes. So FH is perpendicular to EG. And then the last piece is that they are bisectors. So in order to find out if they are bisectors, we need to find that midpoint where they would meet. And honestly, I don't even need to do that because I just proved in this statement that they are rectangles, or that this is a rectangle. And in this statement, I just proved that it's a rhombus. And so because we have a rectangle and a rhombus, we get to say that it's a square. So I don't actually even need to do that diagonals are bisecting, because if it's a rectangle and a rhombus at the same exact time, it is a square. Sweet. So kind of a lot of work for that one, but that is how it works. So this is also called coordinate geometry. It's kind of a very lengthy process usually, but also a lot more physical. And so you can actually see that this is here. You can not necessarily take out a ruler, but you can measure all the sides by using certain formulas. So hopefully that feels a little bit more like knowing it's a square. Alright, and so that is our set of notes for 6-4. Remember that you also have this sheet that I had at the back here, so that you can fill in this kind of properties of four-sided polygons as well. So that sheet is there on HeadRush for you to kind of fill in, as well as what we did today here. 90-degree angles and diagonals are congruent, as well as our rhombus ideas.